is a research scientist at Department of Biosciences at University of Bari, Italy. He is interested in working on past demographic events and different human populations. Um, by analyzing modern and ancient genetic data. Interesting thing about the investigator is he is aiming at accepting genetic role of complex behavioral traits in abuse and use of substances.
Hi, thank you very much. So the challenge here is to beat one on speed, so I will skip my presentation. Today I would like to introduce you some results of some preliminary data we are analyzing, and the project is about assessing ancestral components, ancestral composition using principal components analysis. We don't speak on GWASs, sure, but Thomas yesterday suggested and made the point that understanding the genetic variation is very important to make proper translational medicine like GWASs. And given that this is an initial step of all the process you are seeing here, even a small mistake can propagate with big consequences. As for example, as you all know, if you use a GWAS made on European samples and try to predict age of other populations, we might end up concluding that Africans are among the shortest people in the world. Of course, this is not the case, and this kind of errors are actually present in science, in researches. But another amazing reason to understand the ancestral variation of human population is because it can unlock the demographic history of many populations, and for some of them we don't even have anything related to archaeology or to history, and so genetics is really hiding to unlock some of these areas. How we can understand and assess ancestral composition of population. In an ideal world, we will stick to haplotypes, genome-wide data of all genomes, and we will basically try to paint every individual as a combination of other individuals that we are analyzing. And we can also further refine this analysis using what is called mixture fit or non-negative display, which basically takes these painted profiles and further decompose them in other painted profiles. So it's a two-step decomposition. Of course, when we are dealing with ancient, we use this with many times, and I guess Ajay will give you a glimpse how we use for India to unlock some ancestry in India. Of course, we are not living in a perfect world, and so for ancient DNA, it's very hard to use these approaches, and because, as you know, we have a lot of missing data, we usually deal with pseudo-haploid data, and so the most famous and the most used tools is OPR. I will try to go very quick. If we have a target population and two sources, or two proxy of the sources, and other unrelated population, we can use the F4, which Alessandro showed yesterday, to try to summarize more or less this complex genealogy. And basically, we can obtain a matrix made of several F4, and we can use this matrix to decompose the target population in proportions of the two sources. One very interesting paper that appeared last year showed that actually the F4, which is the core of 2PR, are very related to principal components, and so are also F2, F4. I'm not going into detail, but just F2 is Euclidean distance, like F3 and F4 are basically orthogonal projection on F2 distances. And so we asked ourselves, if F4 is the core of QPR, and F4 are very related to PCM, to principal components, can we use principal components instead of F4? And that's what we wanted to try to find out. So we started from a simulation framework. We simulated basically old world, very simplified model, and from these populations, we basically created eight advanced populations with 70-30 proportions, and that means 100 generations ago. And so basically we did the PCA, and we were trying to reconstruct the ancestry of this population using the NNLS and using the best 10 PC vector, both in a population flavor and individual flavor. What we got? What we are seeing here, we see in both the plots two lines. The plot on the left is population-based, and the plot on the right is individual-based. The lines are basically 70% and 30%, the two ancestry proportions for each adult populations. And I start to say that we always get the right populations, so you need to trust me on this. But we also get very nice results in terms of ancestry proportion, both from populations and individuals. Of course, you can see that some populations is not so great. This happens when basically the mixing sources are very close. Basically, the FST between the two sources is something like 0.01, and so it's hard to disentangle the two sources. And then we said, okay, it's working in an ideal setting, no missing data. Let's try to mixing data. So we basically added ancient missing data to our samples. We made them self-deployed, and we used the common method, which is using the modern individual as to infer the PC space and projecting the ancient samples. Also, for with this framework, we got very nice results. I mean, we are still able to get always the first two major sources. Sometimes we get some minor sources, and usually these minor sources are actually the sister branches of the real sources. So it's not very okay, but not so wrong as well. And so we were very happy about it, and we wanted also to actually compare this method with QPR. And also here, the results are very, very similar to, our results are very, very similar to QPR, with a correlation of 94%, very high, very low p-value. And as you can see, the fact that we find some secondary source is also replicated in QPR, so is more due maybe to the fact that sometimes two populations are very close, and so it's hard to disentangle which is the right one. There is one main difference, though, that our analysis takes more or less 1 second to perform, while in QPR we took at least 15 minutes. It depends which flavor of QPR you use, but at least 15 minutes are needed. And so, lastly, we wanted to use this approach on real data. You already saw this line from Shish yesterday, and so basically we are comparing our method with those employed in Lazaridis et al. 2023, which basically reconstructs many samples from Europe, from West Eurasia, using 5 different components. First, we used only 10 PCs, and you can see, the plots are very, very similar. And in fact, our correlation is about 0.9. But if you look at this side, you see that the two inferences are quite different. For some reason, our approach is missing some of what we call Turkish Neolithic component. And so we were thinking what's going on here. And the first thing we tried is to use 100 principal components, which basically adjusted the things, not completely, but this time the correlation is a little bit higher than before. So we believe that our approach is actually very reliable and at least the same reliability of QPR. And I forgot to tell you that this approach performs very, very well even when you use as a source just one individual, single individual, as sometimes is usual for ancient DNA, as for example for Caucasus hunter-gatherer, we have really a bunch of individuals, and performs very well also with high missing data. Does not require an a priori defined left population, source population, and right population. You just put everything well in your estimation, and at least in for our approach, it correctly recognize which are the real sources of populations, and again is very fast compared to QPR. Of course, that's not all. There are some bad things as well. Our approach is not an admixture test. So we were dealing with population that we knew they were admixed. But if you do it with some population that is not admixed, you still have an answer. And so we are thinking to use some F4 estimated from PCA to try to guide the user if the population is admixed or not. And of course, when you do the PCA, you need a good selection of sources and population to infer the principal component space. So if you try to do to use this method using only African populations and one European, you may get not the right answer you are looking for. And at the moment, this method does not provide confidence interval, but that will be quite easy to fix it because we have individuals and also we have chromosomes, and we could actually do PCAs for check-type chromosomes. And we still not very clear in mind if the best approach is to use all the PCs that are available, or if instead we should actually select some principal components that are, for example, the ones that maximize the distances between the two putative sources, because sometimes we have, I don't know, some hint of what are the real sources. There are always some. And I just wanted to thank Luciana, Ludovica, and Alessandro, which are the minds behind this work, but also Luca and Thomas, which are doing their best to challenge ASAP and trying to see if it's actually working. Thanks.
Thank you. The talked about ASAP, interesting comment. You also talked about limitations and the virtues. One second versus that was really interesting. Okay, so open for questions and discussion.
So I see that you covered the the caveats, I just wanted to reconfirm with you. So, uh, will it not tell us the ideal number of sources? That's question number one. So how does it decide between two, three, or four sources, and which model actually is the best? Second, if we have two models, how do we choose between one or the other? Is there a p-value or some? So these are the two questions.
Yeah. So in principle, we do not need to look at how many sources there are, because we put all the sources. So we do not need, in principle, the copy wave approach, which before says how many sources you should use or which sources you should use. We put all the possible sources, even the ones that are completely unrelated, into the analysis. However, we can still, in principle, I didn't implement it yet, but we can still, in principle, see which are the best models. Mainly, if we had, mostly if we have the same number of sources, because again, we are dealing with residuals here. So, in principle, on two four sources models, we should prepare the one that has less residuals, rather than provided that there has not been other approaches.
Just a suggestion for that. I mean, little bit of residual difference might not actually mean that one is drastically better than the other. So, when comparing two models, if residuals are a bit different, you said that the lower residuals should be preferred. My simple point is that that's necessarily not the case, and maybe you need.
Yeah, sure.
Just a quick question. So the source, right? Does the number of individuals in the source and the completeness of the data in the source, will that make a difference here? Because if I look at the EHG and the Marmara samples, right? And also the SRB, their proportion seems to be the ones that are not super correlated. Could that be because we have fewer number of samples or lower coverage there?
I don't think so. I think that the problem here is more that, for example, something Anatolian analytic is reached with Levant. I think that the problem here is more how close they are than the number of individuals.
Thanks for the talk. It's very interesting. The Ben Peter paper was also very interesting. So glad to see that you have implemented it. So my question is, because this reminds me a bit of presentation I saw from Flora Day a couple of years back when she was doing this kind of PC approach and looking at distance between two populations and where the person sits in the middle to estimate a mixture. Is your principle sort of similar in that sense?
I guess yes. I guess they are similar. I think that the approach they were using were a little bit more complex than this, though. It was something about machine learning, right? To try to understand which ancestry.
I can't remember either, but I think it was like using PCA to estimate that mixture proportions.
Yeah, I remember that, but yeah, I cannot say more.
What about the variable contribution? So, if we know the variables which are specific to certain ancestry, how does it matter in this particular technique?
What do you mean as variable?
Ancestry specific markers, when we are choosing them, and then we get a PCA, and the frequency of those markers in those clusters, can we actually use them to choose our source population?
I guess you can do it with ancestry informative markers. Of course, the number of them is usually limited, so I don't know how deep, how fine in scale you can go touch, for example, within continents or something like that. It should be, I should look into it. But I mean, now, the fact that you usually have hundreds of thousands of SNPs, I don't know.
Join me thanking Francisco for the wonderful talk. We'll move on to the next talk now.
Thank you, Francesco, for brilliantly presenting your research work and explaining the use of PCA in deciphering the ancestral components. Now, I would like to invite our chairperson, Ms. Dr. Guru Datta, to offer the memento to our speaker.